Okay, welcome back. What I want to do is to continue with engineering science, okay? And we're looking at unit 2, level 4, okay, which means that you'll be doing HNC or ONC or the T level, okay? Now all I'm doing here now is going to recap, and I'm not going to take too long on this, okay? You've got this already in motor principles and motor principles 2. Okay, I'm not going to take too long on this. You've seen all this already, okay? So just recapping briefly, okay? And that's just there. You've seen this already. I spoke with this to you on this bit, okay? And what I wanted to come on to now is to look at the mechanical power produced, okay? And let's just go in a little bit closer so we can see what we're looking at and dealing with, okay? The mechanical power produced is P equals omega T equals 2 phi nt. Okay. Now remember that if I remember correctly, this value is similar to this value here, if I remember correctly, but don't hold me to that because I'm trying to do it from memory and I could be wrong. So I apologize if I have given any misinformation. Okay, it is not my intentions, but being an old man now, you know, these things happen. Okay, where omega is the speed in radians per second and n is the speed in revs per second. Note that omega equals 2 phi n. Okay, I may not be far wrong from what I was thinking. Okay, but let us continue. And some of you guys will be at this level already, so you might know even more than me. Let's not go out of range, okay? Because I want to make sure that we have this in view, full view, and easy to understand. Or reach to. Okay. Equating mechanical and electric power, we have 2 phi nt equals counting the armature, electromotive force in the armature. excuse me. Okay. EA equals 2 phi nt over IA. Okay. That will be equation 2A. And that's equation 2B. Now refer to these as the relevant equations, because T equals IA equals times EA divided by 2 phi n. And you should know the value of pi. By now, okay? Since T equals K, you know, I cannot tell whether this is a 1. Let's just call it K1 for now. Theta IA, we may substitute into 2A. Okay? By substitution, EA K1 pi phi 2 phi n equals K2 phi n. Now, make sure that you can calculate and compose your equation so that you arrive at this value here. I'm not going to do that for you. You should now be able to do that for yourselves, okay? Now let's look at losses due to armature resistance. Now, wherever you have a motor, there is armature resistance. There's going to be a resistance value which is going to cause you to have heat generated. And this is what you're trying to minimize. The armature circuit has a resistance mainly due to the resistance of the copper windings and brushes. This is denoted RA. The EMF, EA, of the armature is the terminal voltage, V, minus the resistance loss. Hence, EA equals V minus IARA, and we call this equation 3. Okay, substitute into equation 2, which is up here, okay, for EA, and we get N equals V, open brackets of course, V equals V minus IA RA, close brackets, over 2 phi K1 theta. Okay, but again, you will need to put in the values for yourselves, and as we move on, you'll see that we actually begin to implement these values anyway, hopefully. Often the term IARA is small in comparison to V, and a close approximation is N equals V over K theta. I call it theta, you may call it something else. These equations are the basis of the following work. Okay. Now, if it was shown in tutorial 2 that the EMF of the armature, now you ignore tutorial 2 because you have done a lot of work already to be at this level, so you can only look back at your notes. It will be the same for similar work. EMF of the armature, sorry, so let me start again. I apologize. It was shown in tutorial 2 that the EMF of the armature depends on the number of poles and the number and type of windings on the armature. It was shown that E equals Z Pn theta over 60 for wave winding, E equals Zn theta over 60 for lap winding. Now make sure you're familiar with the wave windings and the lap windings. They are a different type of windings, and you'll find them mainly in motors. Okay. Interestingly enough, I looked at this the other day to actually show you what lap windings look like and wave windings look like. But this is something for you to make yourself familiar with and do your own research. For both the only variables for a given generator are the speed N and the flux theta. We could say E equals Kn theta. P is the number of poles, pairs, and Z is the total number of conductors. Z equals number of slots times number of conductors per slot. Okay, so if we go back a little bit here and we look at what we were talking about in regards to the slots, here is where we're talking about the number of coils per slot. Each slot here will have so many coils. The same thing would apply to here. These would then be your slots for your armature winding. Okay, so each slot will have so many, maybe 10 windings or whatever, or more in many cases. Okay, so keeping this in mind, okay, and let me just go back a bit so we make sure we get it all in view. Okay, and let me just go back, make sure I haven't overshot anything that would be relevant to yourselves. Okay. Okay. Now let's look at this here. Work example number 1. A DC motor is connected to a 400 volt supply and takes 40 amps. The armature resistance is 0.3 ohms. The motor has 4 poles, wave wound with 444 conductors. The useful flux per pole is 0.025 Webers. Calculate the EMF on the armature and the motor speed. Okay, we're looking for the EMF on the armature and the motor speed. So we're looking for the electromotive force on the armature. And remember what we talked about when we said armature, we were looking back at this, okay? This is our armature, okay? And so that's what we're looking at there, okay? armature. Clearly states that. So let's go back to where we were. Now E equals V minus IA RA. Now for me, what I tend to do is I normally write this down. So let me just see what I can do here. Bear with me for a moment. What I want to do here is to come back to this, because what I like to do is to actually show you the calculation. Mind you, in saying that, you should be able to do this by now, your level 4s. So V, what's V? So here we have E equals V minus IA RA equals 400 minus 400 volts supply minus, open bracket, 40 times 0.3. Now 40 is the amperage and the resistance is 0.3. So we know that comes from here, and we know that that comes from here, okay? It's important that you know where these pieces come from. Equals 388 volts. So when you times that by that, let me see that we are getting it right, because some of these does come out wrong at times, and I can question that if need be, okay? Okay, now yes, it does work out right. That 40 times 0.3 is equal to 12. 400 minus 12 leaves you with 388 volts, okay? So that, I'm happy with that result. Now, we're then looking for the useful flux per pole, calculate the EMF on the armature and the motor speed. So we're looking for the motor speed. And we're looking at the formula for that is E equals ZPN theta over 60. Now, the has 4 poles, that's 2 pairs, okay? So that there, 4 poles, and we deal in pairs per pole, okay? So you can see that that will be 2. That's where that 2 comes from, because it's 4, and we need to deal in pairs. So we have 2 pairs of poles, okay? N no, sorry, we're calculating the speed, motor speed. So N represents the speed of the motor. So N will not be in this. Well, it's put in there purely as a matter of reference in order to show that what we are trying to find. Now, I'm going to leave that for you to confirm, but you can see that the speed here, N, equals 1049 revs per minute, okay? And you should be able to get that from this, okay? E, the electromotive force, we have it here already, is here. We know that. And we are going to transpose for N actually. That's quite interesting actually. I quite like that. Because we're now trying to find n, and we need to take n out of that. Transpose for n. Basically, that's what you're going to be doing. Okay. But let me just see how that works out for me. Myself, I'm doing this for my own edification. I'm not going to be putting it up there for you. I want you to be doing this for yourselves. Yeah. Okay. Yes. As you can hear the flapping, that's my calculator. Just trying to make sure that what they've said here is correct. Okay. Now let me just check something here for myself. Okay, now I'm on this here for a while because I want to make sure that you have time to look at this yourself and work it out. Okay, so that's where I'm going to stop now for the time being. Okay, and again, thanks to freestudy.co.uk. Okay. Now the way that this is done in some cases is not always comprehensible. So what I'm going to do, I'm going to work on this to make sure that when I pick it up the next session, I will be able to give a wider explanation in most of the cases. Okay, I'll make my business to do that. Now I'm going to see if I could write on the screen as well so you can see what I'm doing overall. Okay, but for now we'll stop there, and thank you for your time, and we will look at motor field windings configurations later. Okay, in the next session. This is motor principles session. This should be session 2. Okay, but I am a little concerned I have not checked my other session. Let me just do something here. Be with me for a second. Let me just check something here for a second. Give me for a moment. I have to go into videos. Okay, sorry. Yes, good. I've got it. This will be Motor Principles free. So I apologize. Again, I can confirm that this will be Motor Principles free. Okay. I just cannot remember the numbering sequence I had applied to the other before. So I apologize. Again, being an old man, these things happen. Okay. So I make no apologies or any excuses for that in any shape or form. Right, thank you. And I'm going to make sure that we can explain these pieces together and how these figures were derived. It's possible some of these don't always take these on face value. You've got to put the formulas in place, and you got to make sure that you're actually doing what needs to be done. Okay, that will be it for today. Thank you for your time. Have a good evening. Bye bye.